In this video, we're going to be talking about how we present our data that we've gathered in tables and figures. So the reason we might want to do that is because once we gather our data, we want to learn about what our data is telling us. So if our data is simply just set in a bunch of tables, it might be hard to figure out what patterns exist among the data and to draw any conclusions. Also, take note that in your capstone paper or any kind of report out on work, whether it's in a paper or in the future, you're going to be required to insert figures to display your data so that others can also understand. So knowing how to create these tables and figures and how to do it correctly so that they're readable is going to be very important in scientific and engineering research. Let's begin by talking about categorical data. Keep in mind that the tables and graphs that we create for each data type might be slightly different. So for categorical data, it makes sense to organize the data into what's called frequency tables. They record the total counts, also known as frequencies, for each category. So let's take a look at an example. This is data that was gathered in 2014 for the movies that were released and what movie genre they fell into. So what this frequency table is telling us, it's telling us that for the action-adventure category, 113 movies were released. In the comedy category, 128 movies were released. And we'll need this information later. A total of 564 movies were released in these four categories. This isn't an exhaustive list, so there are many more categories and there were many more movies that were released in 2014. So know that the total in your frequency table must be clear about what it is that you're looking for. Our total is the total of movies released only in these categories, not all movies released. Okay, so this allows me to get a general idea. I can see that there were more drama movies than anything else, and I can see that the least number of movies was action or adventure. But beyond that, it's kind of hard to make a comparison. So that's where the relative frequency table comes in. So relative, in this case, is talking about percents. So we're able to make easier comparisons within our categories, and if we had maybe 2 years that we were looking at, counts for, it would help us to compare those 2 years because the totals might be different. So here's what a relative table looks like. Okay, so again, we have our categories listed, but now instead of the count, we have the percent. And we know that percents are calculated by taking the count, dividing by the total, and multiplying by 100. So that's how we're going to get our percent. All right, so in this case, it was 113 divided by the total of 564 and multiplied by 100. So now I know that 20% of all movies were action and adventure. So why is this helpful? Well, I can see in my counts that, let's say for, I'm going to erase some stuff, let's say for comedy, I had 128 movies that were released, and in thriller and horror, there were 132. I can see those numbers are different, but what the relative does for us is it tells us really, well, how different are they? I don't know, let's look at the percents. 22.7% versus 23.4%. Is that very different? Not really. Okay, so that's where relative helps us. With categorical data, we have several types of graphs that we can also create. So we have bar charts, which are created from our frequency table. And the way to create a bar chart, and I'm sure you've seen these before, is along what we would consider the x-axis. We're going to put our categories. We're going to put, I'm just going to call it AA for action adventure, comedy, drama, and thriller, horror. Okay, and we're going to label that axis movie genres. And on the vertical axis, we're going to put our counts. Okay, and so we need to kind of break our axis up a little bit. We see that our counts go all the way up to 191. Maybe I'll make mine go up to 200. I'm going to split my axis. Okay, we're not doing a very exact graph right now. I just want to give you a sense of what they look like. So each of these is essentially a bin. Our bins don't, in a bar graph, touch one another. Okay, and so we're going to look at action and adventure, and we know that 113 movies were released in action and adventure. So I want to draw a bar that goes up to 113. Again, this isn't an exact process right now. And then for comedy, we're going to go up to 128. For drama, we're going to go up to 191. And for thriller, horror, we're going to go up to 132. All right, so this just allows me to get a good visual of how my data kind of is distributed. Okay, so that's another term that we want to talk about, the distribution of data. So if we ask for the distribution of movie genres over 2014, all we're reporting are the counts. We would say 113 were action adventure, 128 were comedy, 191 were drama, and 132 were thriller or horror. That's what a distribution is. Okay, so we can either discuss the distribution using the numbers, or we can look at the distribution and we can visualize and see, wow, drama had more movies than any other category. Okay, the next type of graph that we can make is a pie chart. And again, you've probably seen these before as well. So with a pie chart, we're going to look at the percentages. All right, so a pie chart is simply a circle broken down into pieces. And again, this won't be a perfect graph, so we're just going to eyeball it. But if we were to look at this, we can see that thriller or horror is going to be approximately a quarter of our graph. At 23.4%. We can see that comedy will be also approximately a quarter, but just a little bit less. At 22.7%. And that action adventure is a little less than a quarter at 20%. And that the remaining 33.9% is drama. Okay, the other option you could also choose, instead of putting in the percents, you could choose to directly put in the number. You could say instead of 33.9%, 191, you could show the count in there. Okay, so that's another option to include the counts. But either way, usually these are colorful, and you'll have each of these areas will be, maybe this one would be blue. This one would be lighter blue. Okay, but you're rarely going to do these by hand. There's going to be a later video that's going to show you how to create these in Excel so they look really nice. But this also helps you see sort of the breakdown. We can by looking at this, we can see, oh, it's really not that different. All of them are taking up approximately a quarter of the pie. But if you had maybe one where it was very extreme, you'd be able to see that visually. So what do we want to keep in mind when we're creating some of these pie charts and bar charts? One, the data has to be categorical. This is the kind of data that we're talking about for these. We're going to see another graph later for quantitative variable that looks a lot like a bar chart, but has very different ways of reading and understanding it. Second, make sure you're referring to enough individuals. So let's say you surveyed 10 subjects to report on eye color. And you could end up in a situation where you have brown, blue, green, hazel, right? And within that, you might only have a total of 2 or maybe 4 in every category. That's not going to really give you a great set of information. So make sure you have enough people that you have asked or enough subjects in your study. And finally, there's something called the area principle that we want to make sure that we pay careful attention to. When we're visualizing our data, we need to make sure that those areas that we're using as visualizations really represent the true magnitude of the data. So let's take a look at an example. Here we can see an example, very clever. Often the area principle is violated because we have a very clever graph where we're looking at the percentage of doctors who are devoted only to family practice. Okay, so what we see is instead of a bar, this is sort of like a bar graph. Instead of a bar, we have a doctor. Okay, but in order to keep the proportions of the doctor the same, the entire area of the doctor has to change. So we notice that while for here it's 27% and 16% is smaller than that, the height is the only thing that should be changing, but the width is also changing. So it doesn't really give an exact relationship between the two. In fact, this doctor looks significantly smaller than this doctor, but the comparison is just 12 to 16%. There really shouldn't be that great of a difference. So be very, very careful about changing your areas. If you're doing a bar graph, your bars should always be two-dimensional and in dealing with simply height. Okay, so when I say two-dimensional, what does that mean? That means that I do not, in a pie graph, you might see those fancy pie graphs in Excel that look like this. Okay, they're trying to show it to you from an angle, but notice what happens. Okay, I've actually divided that up into 4 pieces, and my idea was that those are equal sized pieces. But what about this one area in the back compared to this area? If they both represent 25% of the data, does it actually look like that? Doesn't this one in the back look teeny, teeny, tiny in comparison to this one right here? So each of those areas is not correctly representing what it should. So we want to stay away from 3-dimensional graphs or anything where more than one dimension is changed. Okay, so let's look at the situation where we might not be doing univariate analysis. What about the situation where we're gathering information about 2 categorical variables for every subject? Remember, this is called bivariate analysis. Okay, so let's imagine a scenario where we go out to a parking lot, maybe at this school, and we count the car origin, like is it an American car, is it an Asian car, and who owns it. So is that owner a teacher or a student? We're going to organize that information. Let's take a look. The way when we gather the data, we might organize that information into an easy to collect data table. So I might have car 1, and I might look at the owner, and I might look at the origin. So maybe for car 1, the owner is a teacher, and the origin was that it was American. For car 2, maybe the owner is also a teacher, but that is a European car, okay, etc. So we're going to go out and we're going to gather all that information, but once we have it, it's not really easily understood. I want to see some relationships there. So what we do with that is we create something called a contingency table. So a contingency table takes all of that information that we gathered and it tallies it up. So what we'll see here is that maybe in our parking lot, we had gathered a total of, we looked at a total of 195 student cars, looked at a total of 164 staff cars, okay, and we might have looked at 212 found 212 American cars, 45 European, and 102 Asian cars for a total of 359 cars. Okay, so I might want to take all that information and figure out, well, how did they break those down within each category? That's a contingency table. It shows how the subjects are distributed on each variable. Remember, this is my owner variable, and the categories are student or staff, and this is my origin variable for their car, and it could be an American, a European, or an Asian car. So I'm summarizing the information that we gathered. So what can we do with a contingency table? Well, we can look at what's called the marginal distribution. That's the frequency distribution. Remember, frequency is like saying counts. Okay, those are the counts of the totals of a variable. So we just calculated all of those. Okay, so if I want to look at the marginal distribution of owners, okay, I'm looking at the total counts for all of the owners. So I would report that there were 195 student cars and 164 staff cars. Okay, and I could do the same thing for the marginal distribution of origin. I could report that there were 212 American cars, 45 European, and 102 Asian cars. So that's what a marginal distribution tells me. Think about margin. What are the margins of your paper? They're on the outsides of your paper. Marginals are your totals. Okay, but that's not the only thing that we want to look at. We also might want to look at our conditional distribution. Okay, so that's the frequency distribution. That's the counts of a variable that satisfies only one condition of the other variable. Gosh, that's really confusing. What does that mean? That means that if I look only at one category of origin, let's say American cars, I might want to know what the distribution of owners is. So the question might be, for American cars, what is the distribution of owners? Okay, so the way to break that down, it's saying for American cars, I'm contingent. I'm only looking at American, that should say American cars. And I want to know what's the distribution of owners. How does that category break down? So the way to answer that question is to say, for American cars, there were 107 student cars and 105 staff cars. Okay, so conditional distributions are within your table. Marginal distributions are in the margins, are the totals outside your table. So one natural question that might arise from this type of table is whether there's some kind of relationship between the owner and the origin of these cars. So are students following and staff following a different pattern from each other as far as the types of cars that they own? So one way to do that is to explore to explore the relative conditional and marginal distributions. So remember, if I know my totals, 212, 45, 102, and I'm going to do this one specific way, you could also do it in columns, then I can calculate for each category. Within each category, I can calculate the percent of American cars that are owned by students. So percent of American cars, that means out of the total of American cars, which is 212, what percent are owned by students? Well, that would be 107 out of 212. That's 51 versus 49. And I could do the same thing for European. If I take 33 out of 45, I'm going to get 73%, and 12 out of 45 is 27%. So what I know is that of those owners of European cars, 73% are students. Of the owners of Asian cars, 54% are students and 46% are staff. Well, how does that compare with my marginal relative distribution? How does that compare with my relative marginal distribution of owners for all cars? Well, what we can find out, if we do a little bit of math, we can find out that 54% of all car owners are students, and that's just by taking the total of car owners, okay? And we can find out that 46% of all car owners are staff. So we would expect within each of these categories that there's slightly more student owners than staff owners. Well, that makes sense, okay. So when I look here and I look in the Asian row, I can see here that it follows exactly my marginal distribution. I can see exactly that the breakdown is the same. So that's what I would expect. But if there's something else going on, like there are with European cars, I might start to question whether there's a relationship. So I'm expecting that 54% of car owners are students. But when I look in the European category, a whopping 73% of European car owners are students. So that's more than their allotted breakdown. So they're only 54% of the total population here. So now a lot of them seem to own European cars. That's starting to tell me that students might prefer European cars. So if I see any differences in these relative distributions, I'm going to start to say there is an association, or there appears to be a relationship or association between owner and car origin. Okay, and I would point to those distinct differences. Students are more likely to own European cars. Okay, and so if all these distributions had been 54 to 46, 54, 46, 54, 46 in every category, then I would say there doesn't really appear to be a relationship. I expected there to be 54% of students in every category, and it could have been like that, but in this case, I seem to have some difference from 54%. So it looks like there's a relationship. Now let's talk about quantitative data and how we can look at it. Before we begin, let's recall that quantitative data are numerical, which means they're hard to express as tables because they don't naturally fall into specific bins or categories. Okay, well, so if we want to give the distribution of the variable, we have to create our own categories. And if we have numerical data, our categories are created by simply creating equal width bins. So we might say every outcome that fell between 0 and 9, that could be a bin. And then 10 to 19, and then 20 to 29. It just depends on our data, but each of these would be a bin, and we would count how many outcomes fell within each of those categories. So we're creating our own. So let's take a look at an example. So we're going to look at Wayne Gretzky. Okay, so during his 20 consecutive seasons in the NHL, he scored 50% more points than anyone who ever played professional hockey. He accomplished this while playing in 280 fewer games than Gordie Howe, the previous record holder. Here's a number of games that Gretzky played in during each season here. Okay, so we see a series of data. It's not really telling me much. I don't really know what this means. Maybe I want to know something about how many games on average he played, or what was his usual, or what was extreme value for him. But looking at just the list of data, I'm not getting a lot of information here. So in order to solve this problem, we create something called a histogram. So let's go back to this. So let's take a look at what a histogram does. A histogram displays the distribution of counts per bin. So it's kind of like a bar chart. Okay, so we have some bins or some categories that we create, and then we count up how many of our outcomes fall into that category. Okay, so if we go back to our Wayne Gretzky data, we need to create some bins, and then we're going to count how many of the outcomes fall into those bins. So we're going to make a quick histogram right here. So let's take a look at our data to create the bins, and you'll see in a later video that you can do this easily in Excel. But we want to take a look at our smallest value, and it's helpful also to know what our largest values are. Okay, so it looks like our data ranges from 45 to 82. So what are some natural bins? Maybe we'll make a bin that we'll go by fives. So we'll have one bin that goes from 45 to 49. And we're going to go 50 to 54, 55 to 59. See, all these bins are an equal width. 60 to 64, 65 to 69, 70 to 74, 75 to 80, and then, oops, sorry, not to 80, to 79, and then 80 to 84. And that should cover all of our data. So now that we have our bins that are all the same width, we want to count up how many values fall within each of those. So let's take a look. And I'm just going to cross them off as we go. So how many values are from 45 to 49? We have 1. And that's it. Okay. 50 to 54. So let's look. We've got, not seeing anything that starts with a 5. Oh, sorry, I forgot 48. We had 48 here for the last one. I'm not seeing anything in the 50 to 54 range. 55 to 59 range, I'm also not seeing anything. Okay, so it looks like we're going to have a gap in our data. 60 to 64, I have a 64 here. 65 to 69, I'm not seeing anything. 70 to 74, I have a 74. 73, another 74, and a 70. And then 75 to 79, I have a 79, another 79, 78, 78, and the remaining values fall in the 80 to 84 category. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 values. Okay, so now that we have our tallies, how many counts there are within each bin, we can make our histogram. So again, a histogram looks very, very similar to a bar graph with some unique properties. So notice remember when we talked about ordinal categorical variables, we've essentially created a category that are ordinal. You would always put 45 to 49 before 50 to 54. That's just what a normal person would do. So since they flow right into each other, our bins are going to be right next to one another. That's different than a bar graph where the bars were separated. Here our bars are going to be attached. So I can just break up my axis by saying 45, 50, 55, 60, 65, 70, 75, 80 to 85. And what I just need to remember is that the 45, that goes into the bin after it. So 50 goes into the bin after it. Okay, so that's just one point of remembrance. That's why it's nice to do this count here. And then so this is number of games per season, because it's important to label our axis. And then on the vertical axis, we're going to put counts. So when I look at my counts, I see that my maximum count is 9, so maybe I'll just go up to 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then I just create my bar. So I'm going to make my bar go up to 2 for the first bin. And then I have no bar for 50 to 55, no bar 55 to 60, and then in this bin I have just 1. And then I have no bin, and then or no bar, and then I have a bar that goes up to 4, another bar of height 4, and then a bar that goes all the way up to 9. So now I have a pretty good view of my data. I can take a look at my data and I can say, wow, it looks like, you know, he was most likely to be playing 84 games, but he had some seasons, maybe he was injured or where he played fewer games. So I can get a good sense of what my distribution looks like through a histogram. So just like with categorical data, there are some things that we want to keep in mind when creating graphs for quantitative data, specifically histograms. First, we want to make sure we're dealing with quantitative data. So since histograms and bar graphs look very similar, we need some mechanisms for making them look different so we know what kind of data we're dealing with right off the bat. So make sure we're dealing with quantitative data. Carefully label your axes. It's important. I did some quick histogram on the last slide, but you want to make sure when you make your histograms that your axes are carefully labeled with what they're measuring and include any units if that's important. And again, a histogram looks like a bar graph, except the bars are touching. We cannot violate the area principle, so we can't be doing with a histogram. There's no, three-dimensional bars, right? Nothing like that. Even if you think it looks cool, okay, we're not doing that, or we're not going to make a bar that's like a person or something like that because it's going to throw off the area principle. So this is bad news. We're not doing that. Okay, so now that we have learned how to create a histogram, we need to talk a little bit about how we're going to describe it. What do we get to say now that we can see our data in a picture? How does that help us understand what's going on with our quantitative data now? How can we get to know our variable a little bit better? So in order to have this conversation, I'm just going to draw a little histogram. It's not going to be perfect. It's not going to have any axes labeled. You know that that's a requirement, okay? But in this case, I'm just going to do a quick sketch. Okay, so I've got my bars here. And there it is. Okay, so this is the histogram we're going to describe. So when describing a histogram, we want to first talk about its shape. So when we talk about shape, there are a couple things we want to mention. We want to talk about the histogram's modes and symmetry. So let's talk about modes a little bit. You might remember when you first learned about measuring center, probably in elementary school, you talked about mean, median, and mode, okay? And mode was the category that had the most that had the most outcomes. It's kind of similar here. So a mode is almost like a bump. So when I look at my histogram, often what I'll do, I want to get like an overall picture of what this shape looks like, so I'll just kind of smooth it out a little bit for myself. Okay, so you see that green line that I drew on there? That's going to give me an overall shape of what my histogram looks like, okay? Because I don't want to get caught up in all these small little bumps that I have going on here. I just want to think overall, what's the shape of my histogram? If I zoomed out, what would I think that looked like? So when I look, I think I've got one big bump in the middle, right? Seems to overall go up and then come back down. Okay, so it looks like it has one mode, one bump. That's called unimodal. Okay, some other options that you could have. You could also have bimodal. That would have two bumps. Anything more than that would be multimodal. Okay, you're basically talking about how many different centers does your histogram have. So in this case, we're looking at unimodal. And then we want to talk about symmetry. So symmetry means that there's some dividing line, and on one side and the other side, they basically look similar. Now, our symmetry doesn't have to be exact, doesn't have to be perfect, but overall, if I look at this and I draw a line on here, can I fold my computer, I guess, in half and have the same thing on both sides? Not really. In this case, it's not symmetric. So if it's not symmetric, we say that it's skewed. Okay, so to tell which way that it's skewed, because it could either be skewed so that it tails off over here, or it could be skewed so it tails off the other direction. So is it skewing high or is it skewing low? And so in this case, we have one that is skewing to the right. It's skewing to high values because its tail is where it skews. So where you have the thinner tail is where the skew goes. But again, your alternatives are, it could be symmetric. It could also be skewed to the left. Another option is you might have a histogram that has no modes, but is perfectly symmetric. That kind of histogram might look like this. Okay, see how it really generally has no modes, it kind of goes status quo all the way across? You would call this kind of distribution uniform. It's going to automatically be pretty symmetric, and it doesn't have any specific hump or bump that you need to talk about. All right, so we've talked about shape. The next thing that we want to talk about is center. So with center, we're going to talk about some different ways to measure center, very specific ways that you can get a number later. But at this point, you just want to think about, maybe where approximately would my histogram balance. Okay, so I'm looking at where is the middle of the distribution, and for now we can just kind of give it a guess. I have no numbers here, so we're not going to do it here, but where's the middle of the distribution? Okay, and we'll say later we'll learn multiple ways to measure. Okay, and finally spread. So how spread out is my information? Do I have a really wide histogram or a really narrow histogram? And we're going to learn some specific ways to measure spread, but when you're measuring spread, you're thinking about, okay, I have this center value. Well, how different are the other values from that? That's a really important measurement in statistics. And later, again, we'll use the same star. Later, we're going to learn some ways to measure this specifically. And actually, a measure of spread is difficult to talk about unless we're talking about a comparison, as far as histograms go. So both of these with histograms are useful for comparison. So useful for comparing histograms to one another. Okay. All right, and finally, the last one that we want to talk about, this isn't always, doesn't always exist, but we want to definitely mention if there are any gaps or outliers. So are there any values where I don't have any information? And in this case, I have an arrow right there for where our value is. Look, right here, we have a gap in our data, and then we have a value that shows up after that. So that's kind of odd, right? So like it seems like everything's kind of humming along, and then we skip, and then we have a value up here. So that can mean lots of things. And remember, we talked earlier about the context of our data. So, but we just want to mention that, yes, there is a gap at, and then you might just want to say, if you had the numbers, where exactly that gap was. Okay, so it's just like a brief overview of how we describe a histogram. So let's look at a couple of other examples with some histograms that were not hand-drawn by me to get a sense of how we might be able to do make some descriptions. So here, for our histogram, I'm going to draw just the general overall shape so we can start thinking about what it looks like. And we talk about shape and how many modes it has. Looks like it only has one major bump there in the center, so we're going to call it unimodal. And it seems like it tails off here a little bit tighter than it tails over here. So we're going to say that it's skewed to the left. All right, and looking at its center, we're just going to eyeball it right now because we don't have a specific way of measuring it at this point. So we'll just eyeball it. Maybe it's centered right around here. So let's say that it's centered at approximately, I don't know, 70 years. And spread is really difficult to talk about when we're not making comparisons, but it does seem like it kind of steeply goes up here. It does seem like the majority of our values are right around the same number. So we're going to say a relatively small spread. And are there any gaps or outliers? None that we can see. There aren't any gaps. There aren't any values that I'm surprised by. So overall, these are the topics that we want to cover. Let's try another one. So looking at this one, if I try to draw the overall shape, I don't know, I might get something like that. So are we going to describe this as having a mode? It slightly bumps up here, but really not enough to convince me that that's a mode, that that's a place where there are a lot more values than anywhere else. So in this case, I would describe the shape as uniform. Okay, so uniform means pretty much the same all the way across, so there's no reason to talk about symmetry in this case. And once you've described a histogram as uniform, talking about its center and its spread doesn't make a whole lot of sense, particularly with center, because if you want to think about it this way, the center is maybe what you might want to think about as the typical value. Since all of these values have approximately the same count, is there really a typical value? No, not really. So we're not going to be talking about those, nor are there any gaps or outliers. All right, final one that we're going to look at. If I was to try to draw the shape of this, we've looked at histograms before where there are bumps, and I could look at the overall shape here, but I'd really be missing all that space in here. So when I draw our general shape, I'm going to draw it like this. Okay, so notice we're seeing two bumps, 1, 2. So we're going to call this bimodal. All right, and when you're talking about the symmetry of a bimodal distribution, you often look at each mode separately. So are each of these smaller distributions approximately symmetric? I guess so. Okay, so we could say approximately symmetric. Because what's happening in a bimodal distribution is often, these occur usually because there's a variable that is included there that is lurking, we say, that we haven't described. So when we look at these blood pressure counts, and there's two outcomes, is it possible that, I don't know, for example, we don't know who they collected data about, but maybe males and females have different blood pressures overall. So maybe one group is for males, the distribution for males, and the other one is the distribution of females. Maybe there's different ages in there, and that overall younger people have a different blood pressure than older people, and that they fall around the same center. So often when you have a bimodal distribution, it's because you have two different groups that are included in there that have some significant difference. One that we often see might be like shoe size. So you know how males and females have a different set of shoe measurements. So you might see two very distinct distributions in shoe size, and one would represent males and the other one would represent females. Okay, and so for center, since we really are talking about two distributions, two modes, we're going to write the center for each of them. So the center for the first one might be at approximately, I don't know, where are we? 70, 80, maybe 90. And the other center might be 130. So when you have a multi or anything that's more than one mode, you're probably going to have more than one center. And again, spread's pretty difficult to talk about. No real gaps or outliers.